Hello everyone and welcome to a new video tutorial on UMEP, the Urban Multi-Scale Environmental Predictor. Here I already introduced in a previous video what it is the UMEP. Is a plugin that it's open source for QGIS, which is also an open source cross-platform. Today, we'll focus particularly in SOLWEIG. SOLWEIG is the thermal comfort human thermal comfort predictor for outdoor thermal comfort, in fact, using mean radiant temperature. So if you go here to the manual and you choose the processors, and then you go to SOLWEIG, information here is outdoor thermal comfort. So the person who developed this was Fredrik Lindberg in Gothenburg. There is plenty of information on what is SOLWEIG. I recommend you to have a look and read this because there is a lot of research and science behind the tool and the simulation. As any model, it has drawbacks, but it also have a lot of advantages compared to other models, like, for example, simulations like MVMet or like Ladybug or for Grasshopper, etc. Particularly, this plugin works using GIS and remote sensing data, and it's based on mean radiant temperature. So I want to just to summarize briefly what it is the model, what type of spatial data is using, what type of meteorological data is required, and what type of human exposure and environmental parameters need to be incorporated in the model. If you go to the tutorial here, this is the SOLWEIG tutorial at the bottom. We will be using the basic data set that is there, but in future, in the next couple of videos, I will show you how to generate your own data sets for any specific location you want or you are interested to analyze or simulate. But that will be in future. So in this one, we will concentrate to understand the model and how to do a very simple simulation and visualization and analysis. So SOLWEIG means or stands for Solar and Long-Wave Environmental Irradiance Geometry Model, which estimates basically mean radiant temperature. So the mean radiant temperature is the amount is the temperature that it's related to the outdoor thermal comfort. It's different from air temperature, it's different for surface temperature. So SOLWEIG is a model that simulates the sort of spatial variations using 3D radiation fluxes in urban settings. And what type of information it uses? It models the information using vegetation DSMs, ground and building DSMs, ground cover, and meteorological data. So if you want to understand more about what is DSM, DEMs, I've done previously other videos in my YouTube channel about it, but also in UMEP introductory video, I introduced a little bit that what it is. So this is from my previous video. I explained the DSM. Basically, it's a combination of ground and building surfaces. Canopy DSM is the vegetation DSM, which includes vegetation and ground, and DEM is only ground. There is also trunk zone DSM, which is only the trunk of the vegetation plus the ground. Okay, so have a look at the video with more detail if you want to learn more about it. But here, from that vegetation information, is derived the sky view factor. So what it is a sky view factor? So if you click in sky view factor, you will get plenty of information, but just to summarize, it defines the ratio of the sky hemisphere visible from the ground. And it's very simple to understand it. Let's go to a very simple representation. So for each point of the ground, there is an angle, and for each point of the ground is calculated the percentage or the amount of sky that is observed from that particular point. So if there are obstructions or buildings or obstacles, the amount of the sky view factor is lower. So this is calculated in the tool from the vegetation, from the building, and the building and the vegetation complete, and there is also estimated the amount of shadows. So how it works, I will show you here. So if you have a canopy, this is, let's say this is a street canyon, okay? Street canyon, and if you're in a street canyon, you have a point. So the amount of the sky that it is observed in that particular angle and direction, it's calculated. So the sky view factor is calculated from that particular point. But what happens if you have a wide street canyon or it's an open plaza? So you will have a much wider angle of the sky hemisphere. So obviously this sky view factor will be lower than this sky view factor. So sky view factor is measured between 0 and 1. Closer to 0 is less sky, to put it in simple words, and close to 1 is more sky. So on top of the buildings, obviously you will have a very high sky view factor, close to 1 or even 1. And the narrower the canyon, the more trees you have in the canyon, the lower will be your sky view factor, close to 0. And here you will have in the roof a sky view factor close to 1. Okay, and with that information, it's calculated the amount of energy or solar radiation penetrating there, also using the shadow information. So the radiation, it's, again, we have a street canyon here. So this model works. We have the incoming solar radiation, short wave. So they call it, in this case, the K. K is the short wave radiation coming from the sun. This radiation is also reflected, but is also absorbed by surfaces. The same happen on the walls. This radiation is absorbed, retained by the surface, also reflected by the surface. Of course, so when we have dark color surfaces, okay, or paved building, hard surfaces, then we will have a dark color. They will have a higher absorption, less reflection. And when we have light color surfaces, including vegetation, plus cool materials, for example, it can be cool roofs, cool roads, etc., cool pavements, then you will have a more reflection, less absorption. So this is calculating K down, K up, as K down is the amount that incoming solar radiation that it is going into the street canyon, and K up is the amount of solar radiation that it is reflected into the street canyon. But then we have the long wave radiation, and here is calculated as a down, side, and up. And the long wave radiation is basically the radiation that it is emitted by the surfaces. So the long wave radiation is the amount of radiation that it is emitted by the surface. Dark color, obviously paving, concrete will absorb more heat and they will irradiate, is the amount of irradiated, okay? Irradiates more towards the environment, make it warmer. And on the other hand, you have the cool materials, for example, because they absorb less heat, the long wave radiation from these materials will be lower. Okay, so with this information is calculated the mean radiant temperature. But also it's important the shadows. So another information that is calculated is the height of the building and the aspect of the building, and I will explain that a bit later. Then we use ground cover, obviously because of the different type of materials, and then meteorological data that I will explain as well. So as a first step, you have to download the data sets. In the next video, I will show you how to generate your own data sets, LiDAR from LiDAR. You can have DSM, DAMs available from repositories as well, but here you can go to the repository and download the data. We have it in the previous video as well. And now I will show you what I did with that data. So if you come here to data sets, you unzip, extract it all, and then you have here all the data provided by them. This is ready. I will teach you in the near future how to use that data. So we go here to QGIS. The UMEP is already installed. Check my previous video on how to install. We go to our folder. This is UMEP folder, datasets. So we start adding the data. As I showed you before, we start with the DEM, which is the elevation of the ground. Then we go to the DSM, which is ground plus buildings. And if you double click on them, you go to source, you can see there is already assigned a coordinate reference system. Okay, but when you add the canopy DSM, you will get this exclamation mark. This happened before to us, or this question mark. It means that there is unknown. And you can choose it here from the list, or you can choose it using the reference systems that was already mentioned here. Or you can double click and then choose here from the list as well. So usually the first raster or shapefile that you add to the layers, it will dictate the current um, reference system or projection. Okay, so that's why we got it automatically here at the bottom. Or you can choose these coordinate systems if you know, and then you add the DSM and DEMs, and if they have a different coordinate system, you will have to reproject them. Okay, this is very important, otherwise you will get errors. Another very important aspect, and I will emphasize in future videos when I want to teach you how to generate your own data, is that all the data has to be aligned properly. So all the number of pixels and the resolution of the rasters have to be the same. Each raster has to be the same. Okay, same number of pixels. If you go to information, width and heights, 234 to 23, and resolution of 1 meter, it has to be the same, 132, 34, 234, 223, float 32, 1 by 1 meter. Okay, as you can see, these all coincide in width, in height, and pixel size. Otherwise, it's also the model doesn't work properly. We add also the land cover. Um, the land cover in this case, it's represented from 1 to 0. Double click on that and load the style. The styles are provided in the data set. So you can get the style here. If you go to the symbology, 1 represents paved areas, buildings 2, and so on. Okay, so you have here the basic data. Let's keep that basic image for now. And let's save the project, and we can call it intro SOLWEIG basics. Okay, we go to UMEP and we put it there. Okay, so when we have done this, what I'm going to show you is how to run a very simple SOLWEIG simulation using these data sets. Okay, so to be able to run the model, you need to have additional spatial data sets. Let's open the model, processor, outdoor, SOLWEIG, and then as you can see here, you have the building and DSMs. We need to generate the sky view factors. We need to generate the wall aspect and wall height. And then we need to have the meteorological data. And another environmental aspects or parameters that are really important to consider are the environmental emissivity and albedo. Okay, so emissivity is the amount of emissivity of the material. So emissivity is the rate of the energy radiated from the material surface to the atmosphere. Okay, and the perfect one is the black body. Okay, so dark color materials emit less energy or thermal radiation. Um, they absorb a lot more. Okay, so the emissivity, as you can see here, for example, of the wood is very 85, but the aluminum 0.07. The aluminum and then the water is 95. It's very high emissivity. Vegetation close to 1. As you can see, it's very high. Okay, so that's the emissivity, is the amount of, or the ratio of the energy radiated, is the amount of energy that will be radiated to the atmosphere. Now it's different from albedo. The albedo is another important aspect. Well, this is funny, but anyway. So albedo is the proportion of diffuse illumination. If you go to Wikipedia, it's much easier. So albedo is the different sort of um, index. Albedo measures the amount of diffuse reflection. So let's imagine high albedo, it's close to 1 or 100%, and obviously are more reflective, reflect more sunlight. So the emissivity is the amount that emits, irradiates. The albedo is the amount of energy that is reflected. Okay, that's the difference. And the model uses these two aspects. So emissivity of walls are by default 0.9, assuming it is concrete or brick, and the albedo of walls is around 0.2. So this is the emission, and this is the reflection. Okay, so one particular, this is very important to mention here, is that I run, for example, in this simulation tool, cool materials. Cool materials means that the albedo is really high. Okay, it's reflected, so it's closer to 1, for example, 0.7. A cool material, a cool roof. But what is the problem? The model assumes that there is more energy reflected into the canyon. So if you have a narrow street canyon and a cool material with a high albedo, you will have more energy going into the street canyon. And this is assumed by the model as there is more energy, and obviously your mean radiant temperatures will be higher than using a low albedo. In reality, it doesn't work like this. This is not the real world. In the real world, you have a cool pavement or a cool roof, and the environment will be cooler. This can be properly calculated in MBMET, for example, but Solvay has this sort of drawback. Hopefully, will be improved in future. But this is based on my experience. Other researchers may have done more research about it, may have found other results as well. Okay, but there are plenty of papers on this online. So having said that, we go to the Solveig. We need to generate first the skyview factors. So how we generate that? We go to preprocessor. Preprocessor, we go to urban geometry, skyview factor. So in the skyview factor, we need to choose the building and ground DSM. We can include also the vegetation if we have it, and we include here the canopy DSM. The transmissivity of light refers to the amount of light that goes through the vegetation, and the percentage of canopy height, it's the distance between the trunk and the ground. Now, you can have that information. You can generate it as well in the processing and then add it here. But what I suggest, use the default for now. And if you have the trunk, you need to use here a trunk DSM, and this will be grayed out. Otherwise, you just calculate the average percentage of canopy height for the vegetation in the area of analysis. Keep it with the standard 3% and 25%. We can use the method of 145 shadows instead of the 655. It means less reduction, less estimation, and this is required for anisotropic sky estimation. But let's keep this out of this tutorial. Then we select a folder. We can put outputs and then create a folder called Skyview Factor and select that folder. Okay, create a folder that is only for your Skyview factors, and then we add the result to the project. We run it, and then let's wait. The Skyview Factor is a time-consuming process. So the higher your resolution, the smaller your grid, the longer it will take. The larger the area, the longer it will take. The coarser it is your spatial resolution, and the smaller the area, the faster it will be. As you can see here, it's taking quite a bit of time. Okay, so another thing that is important is the Skyview factor will be calculated for the building separated from the vegetation and then average together. So what you're going to get here in the layers view will be the average, but in the folders you will have all the sky view factors estimated. I will show you that when they are ready. So here we are, they are ready. It took approximately 2-3 minutes. Let me turn off this, and then you have here the sky view factor overlaid to the land cover, okay? Because it's the transparency. You can change the transparency as you wish. The sky view factors, I want you to inspect the sky view factor using this tool. And we go to the current layer and you just click here. So the sky view factor is right now 0.46 here in the middle of the park. Notice under the tree 0.02. So under the tree in a narrow canyon, as you can see, the sky view factor is closer to 0. On the roof, exposed to the sun, the sky view factor is close to 1. Or in a wide open canyon or in a plaza, it's halfway because you have still shade, obstruction, no shade, obstruction from buildings and vegetation. Okay, so that it is the sky view factor. If we go to the outputs sky view factor, we open the zip folder. You can see here the sky view factors were generated for the buildings and for the vegetation separately, east, north, south, and west in cardinal, all the cardinal points. Okay, you can also access here in outputs sky view factor, the zip folder. This is an advantage of QGIS. You can access zip folders and you can add information from zip folders, something that you cannot do in ArcGIS, for example. So we remove this. Okay, so we just keep this sky view factor, but now you know that this is just the average. Okay, now the next step for the calculator is the wall height and wall aspect. So that is it's important because this will affect the orientation. So let's imagine you have here buildings and you are, in this case, you are in the northern hemisphere. So the sun generally will move like this between east and west. So you will have these surfaces mostly exposed to the sun. And it's really important to estimate the aspect. I mean, the aspect is calculated in degrees. So it's starting from 0, 90, 180, and so on. And then we'll go in this direction. So if you are, this is in the northern hemisphere. But if you are in the southern hemisphere, is the opposite. Okay, so that's really important because the taller it is the building, the narrower the canyon, and the more exposed to the sun, let's say from the north or the south, depending on which hemisphere you are, you will have a larger exposure of this material to absorption of the heat, irradiation of the heat or emissivity, and obviously different levels of shadow and sky view factor. So these are all the factors that influence on the estimations. Okay, so what we need to do is go here to this again to the processing to UMEP preprocessor, urban geometry, and then estimate the wall height and raster and aspect. We choose the DSM, we calculate the wall aspect. We can estimate the lower limit of the wall height to 3 meters, which is the average for a one-story building. You can reduce it to 2.5 if you want, fair enough. And the output of the wall aspect rate will be, you need to choose a folder. So let's put it in outputs, and then let's put here wall outputs. Okay. Let's choose this folder. And then we put here the name wall. The first one is aspect. Okay. Aspect.tif. Save. So this will be the wall aspect. Now we select the wall height, the same place, output, walls, and instead of wall aspect, we're gonna call it height. Okay, aspect and height. These two, we add the results, and then we put run. So now it's running. This tool is a bit faster, okay? Good, done, we close this, so we can represent it as well with different symbology. The wall aspect, we can use pseudo color, go in Magna, as you can see here, which are facing north, south, east, and west. But if you use the inspector, you will get the degrees. So this is 256 degrees, 346 degrees, 76, etc. And the southern ones, 166. Okay, so that's for wall aspect. Wall height, you can also use a pseudo color and use reds, and then the 0, we're gonna make it completely transparent, okay? So what you see here is the height of the building is 35 meters. This one is, no, sorry. This one is 14, 15 meters, 19, 20, 8 meters. Each pixel varies, of course, because the facade is not continuous unless it's a continuous facade. So here you have 21 meters. Okay, so we have the height, we have the way, the aspect. So now we can go to the UMEP processor. Oh, sorry, UMEP processor SOLWEIG. So now we choose the building and ground canopy, which is the DSM, the sky factor folder. So we go here to the folder and we choose the zip folder. We use the vegetation scheme by Limber and Grimond 2011. That's the name of the paper. We use the canopy DSM. If we have the trunk, we can use the trunk, or we can save to generate a trunk zone. This is what I said before. If we wanted, we do it, not for now. We choose the percentage of the canopy height and the transmissivity of the leaves. And we can use the land cover, which is here, and the DEM here. If you choose use land cover grid to derive building grid, what you're gonna get is a grayed out ground DEM, which is we don't want. We want to use the elevation of the ground. And we save the generating building grid because we can use this later for the analysis to mask areas of building that we don't want to analyze. If we want to analyze the building, the amount of mean radiant temperature at roof level, we don't need to mask the analysis. But if we want to do it, we need to use this grid. Grid refers to raster, it's the same. Wall aspect, wall height. We can use the anisotropic model, but we keep it now. You can read the paper, but for that we will need a shadow map before, okay? And shadow maps, I show you how to estimate that shadows in the previous tutorial. Now we put here the mean radiant temperature parameters if we are assessing a person. I will get back to this later when I show you a second example or second simulation. Now we can use the meteorological data. We can use a meteorological data set provided. They are provided data set here in the from the website. We're going to run that later. For now, we can choose a date, June, July 1997, and then we can change our air temperatures, etc. And we need to edit also here the UTC of set hours, which is 1 for Gothenburg. The local standard time, we want to do the test at 1:30 p.m. We can change the emissivity and albedo if we have that information, and we can store the output maps. We can change also global radiation, direct radiation, and diffuse. All these variables can come also from the meteorological station that is nearby your site. So in the next exercise after this, I will show you how to use a meteorological data set, but in future, I will show you how to generate your own meteorological data sets using Energy Plus files. Now we can output map the mean radiant temperature. Then output settings, we can include POIs, which is points of interest. I will show you this soon. Or we can consider the human as a cylinder instead of a box. This is really important, yes. Adjust emissivity if we want or not. Save it for tree planter. This is for another tutorials, okay? But to keep it simple, we add the average mean radiant temperature to the map. So we have selected all the basics. We consider the posture of the person standing and the basic also default absorption of short wave and long wave. We select the folder. So in output, we create simulation one. This is our first folder, and we run the model. The model runs quite fast. We close this. So this is our initial model. Okay. So if we inspect the values, here is 29 degrees in the middle of the 53 in the area that is not shaded. So it is very obvious. This is at 1:30 p.m. only. Okay. One specific time, 1:30 p.m. on a specific day in June, summer. 29 degrees, the roofs obviously 56 degrees, and exposed areas 59 degrees. So you understand which places will be hotter at that 1:30 p.m. But what happens if you want to do it for a whole day? Okay, so we have here a data set that is already provided, which is the GB 1997, 6th of June 2015A. Okay, so in this data set has been already generated with the meteorological dataset generator at UMEP. I will teach you this in another tutorial, but it's already ready for you. So it has a set of variables here, including rain, relative humidity, wind speed, etc. Okay, diffuse and direct short wave radiation and long wave radiation, etc. So this is the time of the day, 1:0 midnight, 12:23. So remember that SOLWEIG used 24 hours format. And then you have the minutes as well. So this data is ready for you. So let's rerun now our processor using that data set. DSM, let's select the sky view factors, vegetation, canopy, land cover, ground EM, aspect, high. And now we use a continuous data set, which is Gothenburg, this one, the first one, okay? So with this one, there are basic things. The only things that haven't changed are the wind speed and height of the wind sensor and UTC that you have to select. The local standard changed because it will be calculated for any time that is specified in the data, okay? Emissivity of walls, emissivity of emissivity of walls and albedo. As you can see, the ground has changed. Why? Because as soon as you use land cover, this is grayed out. I forgot to mention that before. So why? Because they are already in the model, in the Python, in the model, they already specify values of emissivity and albedo for each type of land cover. But if you don't use that, you have to include that. It have to be specific. Then we select a new folder, outputs, simulation 2, and we add the average and we run it. So it will take longer because it's now generating for the whole day using the meteorological data. So it take a bit, just wait a couple of seconds. It's getting closer. Yep, we're getting there. Okay, I'm not gonna close this just to show you. So here, obviously the symbology is by default, the transparency, okay, it's 100%. So what you see here, if you open here, the no data value is 9,900 minus 9,999. You go to symbology, I want to put from 0 to 70, and let's use the divergent, the spectral, and let's invert color ramp, apply. So as you can see here is the average for the entire day, 20 degrees, 20, 19 under the canopy, 32 on top. As you can see, is different. This is the average for the entire day. If you want to access do the entire simulations. So let's refresh. This is only for the average. So how you can add, let's say, simulate for each time of the day. If you go to the tool, output dataset, sorry, outputs, simulation. So you get only this information. So what you could do is now run the analyzer. Processor, outdoor, SOLWEIG Analyser, and you select the folder, simulation 2, select folder, and you can show the animation. Oh no, it didn't generate it for every single time of the day. Very particular. Why? Usually it should be all of them. Let's do it again. I think I have it open. UMEP dataset, Gothenburg, this one. And oh, we need to save the output maps. That's what my mistake. I didn't put the mean radiant temperature output map. So then it's only the average what it's estimated. But I want to save the shadows. You can save the short wave radiation and long wave radiation. But for now, let's store the output map. So this is really good example of one my mistake. You can also estimate the diffuse and direct shortwave components from the global radiation, which is really good if you use this and you don't have the specific diffuse and direct shortwave component. Let's choose again the same simulation. Let's run it and let's wait for that. So as you can see now, the model was successfully, the mean radiant temperatures maps have been stored. So now we can analyze any one that we want. I don't close this. Look at this. So we have here every hour. So let's imagine at 2 p.m. and this is how it looks. At 4 p.m. this is how it looks. And you click here 58 at 4 p.m., 58 at 2 p.m., etc. So let's remove it now for now and let's do the analysis. Okay, how we analyze this? We use the post-processor SOLWEIG Analyser. We select the folder, in this case, UMEP output simulation tool, and then we can choose the parameter because we saved mean radiant temperature. If in the output you put shadow, you can assess the shadow. If you put short wave radiation, you can assess analyze the short wave radiation. Okay. So let's go to the analyzer and then you can choose here the parameter. We don't have point of interest. I will show you how to do that in a minute. So we show animation. This is 2, 3 a.m., 4 a.m., 5 a.m., 6 a.m. So you can record an animation of the mean radiant temperatures. Okay. The mean radiant temperatures here go from -10 to 70. Okay. Now you can exclude building pixels from the analysis. This is when the building is very important. As you can see, I didn't generate a building grid in this, but the building grid was generated in the previous one. So I will add it here, and this is the mask. One for ground surfaces, building 0. Any other surface is 1, building 0. And this will be used to exclude buildings pixels. So we can exclude building pixels from the building grid and go to, here we go, buildings. Okay. And then we can analyze the diurnal average, daytime average, nighttime average, maximum and minimums, etc. Average of a specific time of the day, if you want. Okay, you have the specific times for any time you have here in your folder. If you have only estimated from 6 a.m. to 6 p.m., you only have that options here. You can establish percent thresholds of temperature, etc., but I don't want that. I want just the basic analysis here and select an output folder. So in outputs, simulation 2, I will put analysis just to have there all the information. Select folder. And then you can add the analysis to Canvas and you generate. Okay, so what you got here, let's close here all these to avoid the average. This is the information we got. Okay, we got the mean, diurnal mean, 9 degrees. This is no, oh, sorry, these are buildings. I'm in the wrong one. I will select this. So here you have 20 degrees. Sorry, 20 degrees, 22 degrees. The representation is not the best. Apply from 10 till 32, apply, and you can see here, and this is 0 opaque. Okay, so then is when you get values here are minus 9,999. Why? Because it's no data. Okay, no analysis. And this is what you got for notice for your analysis. So you can run the zonal statistics if you need it to estimate the average. Okay, you just go here and you can put zonal statistics, or you can put raster raster layer statistics. You can choose the diurnal, and then you can choose your statistics as well, or save it or run, and then you get here the mean. You have to exclude the no data. So you have to export this as a, the problem is that here, source information, then the no data is not selected. Additional no data value. This is, we need to apply. Okay. And then we need to run again. So now we exclude the no data. Otherwise you will get a wrong value. Okay. So now the maximum is 32.7 degrees in the entire raster. The mean is 24 degrees, the minimum 16 degrees. But this excludes the buildings. If we do this from the average mean radiant temperature here calculated originally, you will get also the roofs. I will show you the difference. You go here, and instead of this, we go for the average mean radiant temperature. And let's run it. So you get the different values here. Are close similar, but that is not the correct analysis, because if you are analyzing the public realm, the outdoor thermal comfort at human scale or human height, this is very important to you, the exclusion. Okay, so this is the diurnal. And like this, we have the daytime, we have the nighttime, the maximum, the minimums, etc. So let's do it for the maximum. The no data value is again 9,990,000. This is very important. Symbology, pseudo color, invert color ramp, apply. Sorry, from 0. And we exclude. Okay, apply. So here you will see this is the maximum, 61 degrees, 52. Now you want to estimate for, this is water, for example, 47. So if you want to estimate now the Raster layer statistics of the maximum, you run it, you will get the mean maximum in the entire area of analysis is 52 degrees, and the minimum maximum value is 28 degrees, which is on the top of the canopy. So the hottest moment during the day for the tree canopy, the mean radiant temperature was 28 degrees. So I'm teaching you how to analyze this data. So this very interesting analysis. Now let's run again with this. Let's close the analyzer. With this SOLWEIG, let's run the analysis using POIs. So what is a POI? Is a point of interest. Let's imagine you want to, let's turn on the land cover. You want to analyze this central area in the park and another courtyard here in the middle. So you need to create a POI. So you go to layer, create layer, new layer. Here we put the name POI, POIs, that's it. We can choose the location, which is even better. Here I will put POI shapefile, easy peasy. Geometry type point. Now we don't want set and m values, none, and it is important, the exclamation mark. We need to select the same project text reference, otherwise we're gonna problem. We create a new field. The new field, there is one by default, which is the ID, and I will put it name. It will be text, and we add the new field, and we put OK. Once we have the POI there ready, we start editing using the editing tool. We add 1 point here, and we put number 1, and we put it plaza or park, sorry. And then we can go here, and we put number 2, courtyard. Okay, we have done that. We save, and we stop editing. We can open the attribute table to see park and courtyard. Now we go back to our SOLWEIG tool. We use the same data set. I will show you something interesting is going to happen for the meteorological data set. Now we go to the outputs, mean radiant temperature, exactly the same, but we include the POIs. Okay, and the POIs are there already, and the ID, and we run it, and you will get this information. The wind speed, there is no data values. There is wind speed is required for PET and UTCI, and this is where it comes here, the PET and UTCI. So PET is the physiological equivalent PET index. It's here, physiological equivalent temperature. So the UTCI is a different one. This is so the physiologically equivalent temperature uses information regarding two. Here we go. Age of the person, the activity, the clothing. The higher the number, the higher the number, the more clothing. So this assumes an average. If it is a male or female, the metabolism, and then the weight and the height. So it considers the metabolism of the person, the environmental conditions, and third, the posture or the activity of the person, and also the other, let's say, information of the environment, correct? So that's PET, but UTCI is a different UTCI index. So UTCI is the Universal Thermal Comfort Index. Here you can find the information in the, and is also thermophysiology, is also calculated using the heat exchange, the body, the clothing, and the activity and the environmental. So there are 4 aspects here, okay? Sorry. So if we go here to the value, it needs wind speed, obviously, because wind speed will affect how you're feeling, okay? And we don't have it in the file provided by the UMEP. So if you go to the data set, Gothenburg, and you go here to the file, which is in the text format, as you can see here, wind is not provided. To visualize this better, you open the Excel. I will show you this trick. Then you put open, browse. We go to Gothenburg, datasets, Gothenburg, all files, sorry. And then we choose this one. Go to the limited, go next, space, and tab, and finish, and you will see here the same file. So as you can see here, wind speed has minus 999 values, which is wrong. So what I did is I changed these values, and I will show you again, file open. You can do it manually, you can add your values. Browse. and I created another version of that file with hypothetical wind speed values just to show the limited space on tab, finish. As you can see here, the wind speed now has values. Okay, beautiful. So this is the one we're going to use. So what I'm going to do is I'm going to change here in the SOLWEIG, and I would use another data set that I modified, which is this one, the number 2. And now we run. So now it's running because the wind speed is there. So that's really critical and important. And it will take a little bit as well. So here it is. The software has calculated everything. And without closing this, now they were calculating new average temperature, the same calculations, but what is the difference? Now we have the POIs. So let's open the POI and overlay, and let's choose single labels name. And now let's see what we got in the layer of simulation on the outputs here, UMEP outputs. If you go to simulation tool, then you have POI information for 1 and 2. So POI 1 gives you all this data, all this information, all these estimates, year, time of the day, altitude, azimuth, short wave radiation, diffuse and direct, global radiation, the different angles, east, west, south, and then you have at the very end temperature, humidity, mean radiant temperature, and then you have the PET and UTCI. Difficult to be distinguished here, but you can open it in the same way that I show you with the Excel. File, browse. Let's go to UMEP, output, simulation tool, analysis. Oh, sorry, all files. POI1, delimited, space again, next, finish. So what you get here, it's much easier to understand. So the most important ones, these UTCIs and PETs. So you will notice there is slight difference in the way these two indexes are calculated, but the software is giving you. So it's giving you the mean radiant temperature, which is important. It's giving you the PET and UTCI to assess autothermal comfort of that particular point. So doesn't give you continuous PET and UTCI across the entire area, like mean radiant temperature, but it gives you for each specific point. So if you go to again to the analyzer and you choose the folder, simulation tool, analysis, oh sorry, simulation tool folder, then you can choose the mean radiant temperature. You can choose the POI number 1 and the variable you want to analyze, the UTCI, and include another variable if you want the POI2, and also analyze the UTCI and create a scatter plot. And then so you can plot here this relationship between the two sides, for example. Or if you want to create here an analysis of, let's imagine the air temperature and the UTCI for the same point. You can see here is there is a linear or no relationship. But this is the scatter plot, okay? Just for a scatter plot analysis. But you can also estimate, for example, relative humidity, or if you want to calculate PETs between number 2 and 2, you can, oh, this plot, this is not a scatter plot. You're plotting simply here the values, sorry, number 1 and 2 plot. So you can compare here the PET values from two different indexes. The number 1, oh no, this is the PET from two different places, the number 1 and the number 2, so you can distinguish some differences throughout the day. Okay, here is just plotting the variables, and you can save these as a PNG, TIFF, etc., or PDF. If you put a scatter plot, it will compare the variables between point 1 and 2, how different they are. So that courtyard not so different from the plaza. But then you can choose different POIs and compare. And you can also do the spatial analysis as I showed you before. So these are very useful information. Also, you can add the information to the table for this specific time if you want to, and run the analysis or display the temperatures. But the key one is here. These are the variables that you can use for analysis in any other software package. For example, for statistical analysis, okay? SPSS or um, any other software you got there. It's RStudio. So was the very basic introductory tutorial of SOLWEIG model in UMEP. In a future video, I will show you how to generate your own spatial data with DSM generators, tree generators, um, and how to estimate your own meteorological data for the SOLWEIG. And then you can run this for any location of your preference. Okay, so stay tuned for other videos in future on how to generate your data for SOLWEIG. And so I hope this was very useful for you. Enjoy the simulations and take care. See you soon.